Hello friends, welcome back to our channel. In this video, we will get a glimpse of how STA timing tools work. And more specifically, we will talk about setup time and hold time violation checks. Now without wasting much time, let us get started. Friends, in the part 1, we will discuss about setup time violation check and what does it ensure. And in part 2, we will discuss about hold time violation check and we will discuss what does it ensure. Friends, I have considered this flip-flop to flip-flop path having positive skew, and with the help of this path, we will discuss setup time and hold time check. For the correct functionality of this particular path, if flip-flop 1 is throwing some data on nth active edge of the clock, it must be captured by flip-flop 2 on n plus 1 active edge of the clock. It must not be captured on the same edge, or it must not capture on n plus 2, n plus 3 and so on active edge of the clock. And with the help of setup time check and hold time check, we ensure this functionality only. I mean to say, we ensure that if flip-flop 1 is throwing some data on nth active edge of the clock, it must be captured on n plus 1 active edge of the clock. But apart from this, we also know that there are some paths which are called multi-cycle paths. In those particular paths, even if data is received by flip-flop 2 on n plus 2, n plus 3 and so on active edge of the clock, that is also fine. But to exclude those paths from the analysis, we must constrain them properly. Then only timing tool will exclude them. Otherwise, timing tool will throw a violation and it will inform that if data is thrown on nth edge of the clock, it cannot be captured on flip-flop 2 on n plus 1 active edge of the clock, and accordingly it will throw some negative slack. Let us discuss setup time violation checks first. And we all know that if we want to evaluate my design, whether it will work at a particular frequency or not, we define period constraints. And we also discussed that inside our design, we have to figure out the critical path, and if a critical path works at a particular frequency defined by period constraint, then we can ensure that my entire design will work at that frequency. And let us assume that the path shown in the figure is a critical path. And we also know that for a particular path, this is the equation to calculate minimum period of operation, which is equal to TCQ of first flip-flop plus TCL, that is propagation delay of this combination logic, plus setup time of second flip-flop minus amount of positive skew in the clock path. And from here, we can easily calculate maximum frequency of operation, which is nothing but invert of minimum time period of operation. Now, as per the period constraint and the maximum frequency that is calculated by this equation, tool will throw the positive slack or the negative slack. But friends, now the question arises, if we apply a frequency which is higher than the calculated maximum frequency of operation, what will happen then? In that case, there are two possible cases. In the first case, when setup time of flip-flop 2 will be violated. This will happen if operating frequency is slightly higher than maximum calculated frequency. And the other case is functionality failure. The flip-flop 2 will receive data on n plus 2, n plus 3 and so on active edge of the clock. And that is the scenario where functionality will be failed. And this will happen if the operating frequency is quite higher than the maximum calculated one. And for your information, there will not be any impact on the hold violation because hold time violations are independent of operating frequency. Friends, I have explained whatever I have mentioned in this slide in quite detail with the help of an example in part 1 of the same series. I will share its link in the description section as well as in the I-bar section. You must go through it. Anyway, whatever is the case, if we apply a frequency which is more than the calculated maximum frequency of operation, that is a problematic scenario. So our timing tool ensures that if I have transmitted data from flip-flop 1 on nth active edge of the clock, it must be captured on flip-flop 2 on n plus 1 active edge of the clock only and properly without the setup violation of flip-flop 2. So let me conclude it for you, and I have written it in the slide. The setup check ensures that data should be received on n plus 1 active edge of the clock on the capturing flip-flop if the throwing edge is nth active edge of the clock taken by flip-flop 1. Now this setup check will cover both the scenarios. It should not be received on n plus 2, n plus 3 active edge of the clock, and it also ensures that setup time of flip-flop 2 must not be violated. Now let us try to discuss hold time violation checks, which are equally important to setup time violation checks. And this is the hold time equation, which ensures that hold time of second flip-flop is met properly. THD is the hold time of second flip-flop. TCQ is a delay of first flip-flop from the active edge of the clock. TCL is a delay of this combination logic, and dollar is the positive skew added in the clock path. And this equation is to ensure that the hold time of second flip-flop is met. Let me explain you how. Friends, for the easy explanation, I have omitted skew for the time being, but whatever analysis we will do here will be applicable in case there is a skew available. Now the hold time equation is THD, that is the hold time requirement of second flip-flop, must be less than or equal to TCQ plus TCL, that is delay from this D flip-flop to the input of second flip-flop. Now take your attention on this data path. And what is important here, whenever there is a clock edge on flip-flop 1, at the same point of time, there will be the active edge of clock on flip-flop 2 as well. So the active edge is received on both the flip-flops at the same time. And with respect to that active edge of clock, there is a hold time requirement of flip-flop 2 that the input must be stable after this active edge of the clock for some minimum time. That is called the hold time of this flip-flop 2, and it is THD. So after the active edge of the clock, this input should be stable for THD amount of time. It should not vary. But what is happening after this active edge on flip-flop 1? It has transmitting data from its input to output, and then this data is coming at this input of flip-flop 2. Now let us assume the case if this delay is quite less, even less than THD, then what will happen? This data will arrive at the input of flip-flop 2 even in less than hold time requirement of flip-flop 2, and hold time of this flip-flop 2 will be violated. And this flip-flop may go into a metastable state and cause the functionality failure. Friends, one thing that is quite important and most noticeable thing here, we are doing hold time violation checks at the same active edge of the clock, unlike setup time violation checks where flip-flop 1 was transmitting data on nth active edge of the clock and we were doing setup time violation check on n plus 1 active edge of the clock. But in hold time violation checks, we are doing analysis on the same active edge of the clock. Friends, now let us consider the other case where this hold time equation is met. In that case, that means this delay, that is TCQ plus TCL delay, that is enough to meet the hold time requirement of flip-flop 2. So what will happen? There will be the active edge on both the flip-flops, and input of flip-flop 2 should be stable for THD amount of time. And we also know that at the active edge of the clock, flip-flop 1 will start transmitting data and it will reach at the input of flip-flop 2 after TCQ plus TCL amount of time. And now we are saying that this delay is enough, that the input of flip-flop 2 should be stable for more than THD amount of time. That means hold time requirement of flip-flop 2 will be met. Friends, now let us consider the other case when there is a positive skew available in the clock path. Now both the flip-flops are not going to receive clock edge at the same time. Flip-flop 2 will receive the active edge of the clock after some delay, that is dollar. Now let us assume the case whenever there is an active edge of the clock on flip-flop 1 and flip-flop 1 start transmitting its input to its output and there is a TCL amount of delay, then this value reaches at the input of flip-flop 2. Let us say this TCQ plus TCL delay is so less that it is less than skew on the clock path. Then what will happen? Flip-flop 2 will receive data transmitted by flip-flop 1 on the same edge, and it is a functionality failure. This should not happen. In the other case, when TCQ plus TCL both are comparable to this positive skew, it can violate the hold time requirement of flip-flop 2. Friends, there are 3 possible cases if skew on the clock path is quite high. All the 3 cases are failure cases. Let us talk about the first one, that is called functionality failure. If the skew added is quite higher than the propagation delay of a data path, that is TCQ plus TCL, transmitted value can be captured on the same edge, or in the worst case, if the value of skew is quite higher, the transmitted value can be captured on n-1, n-2 and so on active edges of the clock as well, and which is not expected. It is called functionality failure. As we already discussed multiple times in this video, that if flip-flop 1 is transmitting some value at nth active edge of the clock, it must be captured by flip-flop 2 on n+1 active edge of the clock, except multi-clock cycle paths. So if the amount of skew added is quite higher, then it is a problematic situation. Now let us discuss the last case, which is the most important part of our video. There will be hold time violation if skew added is slightly higher than data path delay, but still hold time equation is not met. In that case, we will see hold time violation on flip-flop 2. Let me repeat one more thing. Whatever hold time analysis checks we are doing on the same active edge of the clock. If flip-flop 1 is throwing some data on nth active edge of the clock, we are doing hold time checks on flip-flop 2 on the same active edge of the clock. And unlike setup violation checks, hold time violation checks are done on the same active edge of the clock. And we ensure that hold time requirement of second flip-flop is met and data is not received on the same active edge of the clock. Let me repeat again. Hold time violation checks ensure that data is not received by flip-flop 2 on the same active edge of the clock and there is no hold time violation. Friends, now I am going to conclude my lecture. In setup check, timing analysis tool ensures that data will not be captured on n+2, n+3 active edge of the clock and there is no setup violation. And in hold time violation checks, timing analysis tool ensures that data is not captured on the same clock edge and there is no hold violation as well. Both the checks together ensures that data is captured on n+1 active edge of the clock without setup and hold time violations. Friends, with this I am going to wrap up this video and I hope that this would be quite informative for all of you. If you also like this video, please press the like button and share your feedback in the comment section. And don't forget to subscribe my channel for all the upcoming videos. Thank you so much for watching.